Thank you for joining Plexon for part 2 of our 5-part webinar series featuring the NeuroLight Optoelectrode. Last week, we heard from Dr. Yoon, who discussed the design and development of the NeuroLight probe. The question and answer session during Dr. Yoon's presentation provided a nice introduction for today's webinar, which will cover technical methods for surgery and recording. Today's speaker, Mishi Borislakos from New York University, will address many of the questions from last week and provide detailed instructions for microdrive assembly and probe removal in his talk, How to Use Micro-LED Optoelectrodes, Surgery, Data Collection, and Micro-LED Control. If you have questions for the speaker, please enter those questions in the Q&A section at any time. Please use the question and answer feature on Zoom rather than the chat feature for your questions. The speaker will address questions live during the question and answer session following the presentation. The webinar and the question and answer session will be available on the Plexon website following the live broadcast.
Okay. Thank you, Nayoka, for the introduction. And I would like to welcome everyone at my presentation, in which I am going to talk about how to use micro-LED optoelectrodes. I am a postdoc at Professor Buzsáki's lab. I'm the visiting researcher at Professor Yoon's laboratory. And I had the great opportunity to test these micro-LED devices with the engineers who made them. And hopefully our collaboration can provide useful tools for us neuroscientists. And the great tool is not useful if we don't know how to use it or we don't have access to this tool. And to disseminate this technology, we held 2 workshops at the University of Michigan, where each participant can perform their own surgery, do the necessary preparations in advance. And here you can see in a couple of pictures where each participant had its own workstation where they could prepare the microdrives, attach the probes to the microdrives, and then the following day they were able to perform their own surgery. So this is a really hands-on workshop. But what is a micro-LED optoelectrode? So we have 2 options. One is the so-called acute probe, and the other one is the so-called chronic probes. And the features for both of them has 32 recording sites, 8 sites per shank. Both of them have 12 micro-LEDs, 3 LEDs per shank. The length of shanks are 5 millimeters, which is great for most of the rodent experiments, but it's quite short for primate or bigger animal experiments. And for the chronic probe, we have a 22 millimeter length of flexible cable, which makes it possible to attach this probe to a microdrive and then move it in the brain. Whereas in the acute probe, we don't have this flexible cable, but this makes it very easy to handle during an acute surgery. And to record the neuronal activity, we can use any extracellular electrophysiology system. To drive the micro-LEDs, you can just simply use a function generator, current source, or the MINT program at the University of Michigan developed the current driver, which I'm going to talk later in my talk. And then the next question is how to hold the probes during recording. So for the acute probe, we can be just as simple as gluing metal bars to the PCB, as you can see here. You need to make sure that you don't attach these metals to any other metal parts of the PCB to short the circuits on the PCB, or you can use our 3D printed acute drive holders. And for the chronic probes, here you can see the very original handmade $1 cost microdrives. We have a 3D printed version, a metal version from companies or from Janelia researchers. And then we developed also a recoverable microdrive. So, and what is a recoverable microdrive? So Sebastian Royer's group designed this in the first time and published in the Scientific Reports journal. And the basic idea is that you have a shell components, which you would send to the skull, and then you have a body and a slider, and you will attach your silicone probe to this slider, and then you can move up and down your probe. And then once you are done with your recordings, you can just recover your probe with the body and the slider. So basically, these recoverable microdrive systems allows probe recovery after a long-term recording, which improves recovery time and probe reusability. And this will save time and money for researchers. And for that original design, we made multiple modifications, but overall, the Microdrive that is available at the Professor Yoon's GitHub page has a 4.8 millimeter travel distance. So this arm can move almost 5 millimeters down, and it has less than 2 grams of weight. And next, I'm going to show you how we can build a Microdrive, attach a probe to the Microdrive, and then implant this whole device into the brain. Okay, so first we need all the 3D printed parts, and then we will glue an 0090 size nuts into this 3D printed stereotactic holder. Here you need to make sure that you orient your nut in this way, and then it will slide into this hole in this component. And then we insert another bunch of nuts into these components. And why we changed actually the original design to use so many nuts is the fact that here we will have a metal to metal connection instead of a metal to plastic connections. So it will improve the longevity of these components. So here again, please note the orientation, how you need to insert this nut. And then once these nuts are in place, then we screw these two pieces together. And then we also insert other screws, both of these components. This screw will hold the head of the drive in place. And this screw mechanism will be used to lock in this component or attach this component to the stereotactic arm. So, and then once those two components are built together, then we can insert another nut into these so-called shell components. But again, you need to make sure that the orientation is right. And this part will be cemented to the skull of the animal. And then this nut we need to seal, basically create a watertight seal. So first we seal it with Play-Doh, and then we cover this Play-Doh with cement. And the purpose of this step is just to prevent during surgery any cement flowing into that nut, which would prevent the recovery of the drive. And then we will insert another nut into the arm. And again, here the main purpose of this to have a metal to metal connection instead of a metal to plastic connection. And this is one other feature that we added to the original design. We added these two metal bars, and this will help to smooth the movement of the arm and also prevent any lateral movements. So, and then once you insert the metal bars into the drive, then you need to remove them a little bit and then glue them in space. So you can see here the removed metal bars, and then you can apply a small amount of super glue or any kind of glue that you like to use. And then you just push it in. And once the glue has cured, then you need to remove any excess metal and glue from the base of the drive, because it's you want to have an even flat surface. And then once this is done, then you could tap the plastic. This is just an extra security feature of the drive. If the metal nut is moving, then you still have some threading in the plastic, which can further support the movement. Then you can insert the front screw. And then we need to attach a nut to this screw. And then once we attach that nut, then we can solder it together, and basically that will create the movement of the arm if we solder these joints together. And during soldering, first we apply a small amount of soldering flux. And then when you solder, you need to be really careful not to apply too much heat to the metal. So basically you just touch it and then remove, touch again, remove. And because if you apply a lot of heat to the metal, then that heat will be spread through the metal to the plastic, and that can melt the plastic. And once this is done, you can test the movement of your drive. If it's good, you keep it. If it's not, then you need to start over the assembly. And once the drive is completely assembled, then you can slide in the drive into the shell component and then secure or lock in with the back screw. So once we are done with the preparation of the microdrive, we can attach micro-LED optoelectrode to our microdrive. And to do that, I personally prefer to attach a metal bar to the plastic omnetics connector. So first I scratch the surface of the plastic just to increase the surface of this connector. Please be extremely careful that you don't want to break your silicone probe during this procedure. And then after you scratch the surface, you apply a small amount of super glue. And then you glue a metal bar into this super glue. And there are others that instead of placing here the metal bar, place the metal bar on the epoxy layer and then you epoxy. There is no consensus about that. One important thing is that this should be a strong connection, because when you plug in the omnetics connector, you create quite amount of force, and this connection should withstand. So once you glued it, then you flip your electrode and lay it down again. I think this is one of the scariest part of this whole procedure. And then basically you could repeat the exact same steps on this plastic surface. So you could scratch the surface and then glue a metal bar again to this omnetics connector. So applying super glue and then just place a metal bar there and let the glue dry completely. And once the glue dried, then we can apply dental cement on these metal bars just to further support this connection. And this dental cement should be liquid enough to flow between the plastic and the metal, but not too liquid when you apply it here to flow to your omnetics connectors. So during the workshop, there were some participants that basically blocked the omnetics connectors. If it happens, it can be removed. It just takes time, and it's better to avoid it. And then you flip the probe again, and then you apply cement on the other side as well. And then once the cement is applied on the flat surfaces, I always put some cement on the side just to create a better connection between the PCB and the metal bar. And then I do this for all four corners where the metal bars are attached to the PCB. And as one of the last steps, you can apply some flux and then solder to the metal bars. So when you are going to solder this to this stereotactic holder and during surgery to the copper mesh, then you don't need to worry about which metal bars you want to use. So and then once the probe is ready, then we can orient, we can hold the drive with a helping hand, and then with another helping hand move the optoelectrode close to the drive. And if the alignment is not correct, then you can move around the helping hand until you see a perfect alignment between your probe backend. As you can see here, it's perfectly aligned with the base of the arm. And once this is done, I highly recommend to move away your probe and then try it again, because sometimes the helping hand can just move a little bit, so the alignment is not correct. But if you confirm that this alignment is still correct, so here you can see before the misaligned version and after the perfectly aligned version. So once the alignment is made perfect, then you can apply a small amount of super glue to the arm. And here again, there are people who prefer Stenta cement, others epoxy. I personally prefer the super glue, but again, whichever you feel comfortable with, just feel free to use that. And then once the glue is applied, then you can just move in your silicone probe backend, and then using a tweezer, you can just fine adjust the position. And here at the backend, there is a tiny layer of epoxy, so you can feel free to gently touch it, but be extremely careful, but this is a safe spot to touch. So, and then once you oriented your probe backend with the drive, then you can let the glue cure. And then we can attach this previously built stereotactic holder with the drive holder. And using this side screw, we secure the drive into this stereotactic holder. And then here we have the metal bar that we can use to solder the PCB to this metal bar. And as a final step, please make sure you don't apply any tension on the flexible cable, and you can align and secure the drive again. So now I am holding this stereotactic holder. I can loosen the screw, realign the drive, and then secure again the whole drive with this screw. And the next step is the surgery. And before surgery, there is still one more preparations that we need to do. So previously we used anchoring screws, but now we replace those with other methods. So we use this 3D printed plastic base, and then we attach to this 3D printed plastic base 6 by 6 centimeter copper mesh, which will later on act as a Faraday cage. And then we cement together the copper mesh with this 3D printed plastic base. And this will be put on the animal's head. So, and then this surgery video is performed on a 3D printed mouse skull, which you can see here. And the very first step that now we are using is using an etching cement, which basically dissolves the calcium phosphate of the bone. And later on, we can cement or use any other type of cements. And using this specific type of cement allows us not to use anchoring screws anymore. So once that cement is cured, then I apply a light curing cement on this metal base, and then we can cement it to the skull of the animal. And why I like the light curable cement, especially for this step, is because once we will hit this cement with blue light that you can see now, in 10 seconds, it's 15 seconds, it's fully cured. So you don't have to spend minutes waiting for the cement to be cured. So once we have a temporary connection, then we can apply quite liquid cement all around. And the purpose of the really liquid cement is to let it flow between the base and the skull. And basically we want to create, again, a watertight seal between our copper mesh or plastic base and the skull. Because if there is any tiny hole in this, and then tissue fluid can leak into this skull, then it can create some unwanted noise issue during the chronic recordings. So once this base is attached to the skull, then we can place a ground screw above cerebellum or any other location that you usually use. really doesn't matter. And then once the crown screw is in place, then we just cover it and seal it with dental cement again. So just to make sure that there is no exposed metal inside here. And then once the ground screw is attached and fully sealed, then we can start drilling the craniotomy. Okay, and then again, depending on your location or your target brain region, you could orient your drive later on, and you can position your crown screw where it's not in the way. So then once we have the craniotomy, then we can lower our silicone probe into the brain. So here you can see this stereotactic attachment is attached to the stereotactic arm. And here you can see the 4 shanks of the micro-LED optoelectrode. And then we can just start moving down into the brain, and be extremely careful to lower down your micro-LED probe at a certain position. It depends on your target location, but you don't want to bump into the plastic base with your shell component. And if you do bump into this plastic base, then you need to lower your silicone probe further down. So, and then once you are above your target location, like 500 micrometers at least, then you can start applying cement between the shell component and the skull and the plastic base. And here, again, you need to use relatively liquid cement to let it flow between the skull and the shell component, but not too liquid, because if it's too liquid, then it can spread into your craniotomy, and then you can just cement your silicone probe. And if it does happen, then just don't worry, try to remain calm, and then you still have a couple of seconds to remove it from the craniotomy. And then you apply cement on the other side. And one extremely important thing is that you want to fill up the space between the shell component and the skull as much as possible. So here you can see this hole before, and then the lack of that it's filled with cement after. And now I'm going to show you like a real surgical insertion. So here you can see the exposed brain surface. You would see in a second the 4 shank of a micro-LED optoelectrode. So once you touch the surface of the brain, you can stop there and measure the surface of the brain. And then you can move up and down until you see all 4 shanks are penetrated into the brain. And one extremely important thing to look at this point, whether all 4 shanks are parallel relative to each other. If you see one of them is bending or not parallel anymore, then you need to stop and then start again, and then see why it's not going into the brain. Maybe there is a dura particle, a bone particle, but you just need to make sure you don't break during insertion your device. And once the device is in place, you seal the craniotomy with biocompatible silicone or wax. And then we can release the side screw from our stereotactic attachment. And then we can start moving it away from the drive. So now this screw is released. And then we can start moving away a little bit. And during these steps, you need to be extremely careful to always pay attention to the flexible cable, because you don't want to put tension on the flexible cable at all. So, and then once you moved away, you can desolder the PCB from your stereotactic attachment. And I personally, again, like to lay down the PCB on the copper mesh where it's not on the way. It seems scary, but I think it's one of the best and safest option, just to lay the PCB down. And again, be extremely careful not to apply any tension on the flexible cable. And once this is done, you can remove this whole stereotactic arm, and then we can start building the copper mesh around the probe. And to build that, we first glue with dental cement some metal bars. And again, depending on your probe location, you can adjust the height, the shape of these metal bars, and then you can create basically any form. And then later on, these metal bars will support the Faraday cage around the silicon probe. So once we have one metal bar secured, then we can move the Omnetics connector and attach the whole PCB to this metal bar. And now the PCB is not in the way, so we can start, or we can keep building all around. And as you see, I again just cover it with dental cement. And as a last step, I put solder on top of these metal bars, which will help or make the further soldering much easier. So basically we are building this metal bar cage around our device. Yes, and then once this is done, we can start folding up and cutting in the custom shape our copper mesh. So basically you just fold it up, you measure, you cut, and this gives you all the flexibility that you need during a surgery. So let me just skip through. And this is again just folding, cutting, folding, cutting. And once this is completed, the one step remained is the ground and reference screws should be soldered to the copper mesh. And you can just pick a spot. Just be careful when you solder your wires, you are not in the way of your screw, or you don't bump into the silicone shanks with any of these wires. And as a final step, you can use your tweezer to smooth the edges of the copper cap. So for example, you could see here there is just like some sharp edges. And if the animal scratches into those edges, they can hurt themselves. So you just gently want to make sure that there is no any kind of sharp edges all around. Okay, and I have a couple of questions from last week's webinar that I would like to address. So whether the chronic probe is drivable or movable once implanted. Yes, if you implant a probe attached to a microdrive, and we will share this video, but for an older version and more details, you could see this other video paper as well. Another question was what kind of anesthesia would work best for the recording? I think urethane is one of the best, but it's a non-survival surgery in that case, or ketamine xylazine is also another great option during recordings. And what is the stability like for acute recording? So there can be some drift, but you can minimize this drift if you insert your probe slowly. And there was a recent paper that showed that the insertion speed should be around 2 micrometers per second during acute recordings. Or another trick could be just once that you are at your target location, wait at least 30 minutes before you start your recording. So you give time for the brain and the probe to settle. And then another option could be post-processing options, because Kilosort 2 can handle drifts very well. So if you use Kilosort 2 for spike sorting, and here you can see each dot is a spike amplitude, and then you can see the drifts, but Kilosort 2 can handle this very well. But to show you some of my data that was collected during these using these optoelectrodes, so here you can see the mean spike waveform and the amplitude over time. And in this case, there was no drift at all. In this case, there was like a sudden drift at this time point. And in this example, there is like a slow drift over time. But again, you have multiple options to reduce these drifts during your recordings. And so what does the data look like? So here we recorded with optoelectrode from CA1 region of the hippocampus, and then we applied a 30 microampere 100 millisecond square pulse on Shank4 LED1. And as you can see here, both light pulse elicited neuronal activity. But please note also these tiny spikes, which are the stimulation-induced artifacts, which is present on all 4 shanks. And but this data was obtained when we used this particular probe the 7 times in this acute animal. So the longevity, especially in acute recordings, is exceptionally great of these probes. And luckily, Khan spent his entire PhD, shown here, to try to solve in an engineering way this artifact issue. So again, we recorded from the CA1 region of the hippocampus, but now we stimulated on Shank3 LED2. And then you can see here the light-induced activity due to a 50 millisecond square pulse. And note the lack of stimulation artifact on all shanks. So this so-called new generation of micro LED probes are basically almost completely artifact-free. And then we also implanted these electrodes in chronic animals. Here you can see the day 1 recordings, the light evoked response on Shank3, and then a day 16 recordings and the much higher intensity stimulation and the evoked response on Shank4. So basically, you could record acutely, chronically with these micro LED optoelectrodes. And for recording, again, you can use any extracellular electrophysiology system. I personally always use the Intan USB evaluation board. And for live stimulation, you could either use a current mode system or a voltage mode system. And why the current mode is a preferred operation is because if we look at the current power relationship of each individual micro LEDs, so here you can see 3 LEDs for Shank1, for Shank2, 3, and 4, and then the current power relationship of each LEDs. Basically, it's fairly, it's a linear relationship between the applied current and the output power of the micro LEDs. However, if you don't have access to a 12-channel independently controlled current source, and current stimulation can be always more difficult, you can simply just use a function generator. And the MINT program is providing also this voltage current datasheet. So one thing that you need to make sure when you use a function generator or any voltage source is that you can apply an offset voltage, which is basically a slightly lower voltage than the turn-on voltage of each individual LEDs. But please keep in mind that this turn-on voltage will change from LED to LED. And then once you set this up, then you can set an upper threshold, which corresponds to 100 microampere. So here you can again set this voltage as an upper threshold. And why this is at 100 microampere? Because you should never apply more than 100 microampere current to a micro LED, because it will destroy the LED immediately. And as I mentioned, still the preferred mode of operation is current control mode. And why is that? Because if you look at the voltage power relationship for each individual LEDs, you can see these kind of relationships, and it's just extremely difficult to well control the power output during a voltage mode. And if you just using one voltage, it's easy, but from if you want to apply double the power, it's not double the voltage. But with current, double the power, double the current will be required. And so now the MINT program at Professor Yoon's lab developed this OSC1 light system, which you can see here. It's basically an FPGA-based current stimulator. But again, in a voltage mode, using just a function generator and a breakout board, you could build your own breakout board. You can see here Sam McKenzie's breakout board that he used at NYU. So for each LED, you can have its own individual connector, and then you can just physically plug in day-to-day whichever LED you want to activate. And so just some features of this OSC1 light controlling box, which was mainly developed by NED, shown here. So it's a 12-channel independent current drivers, and it can provide 1 to 100 microampere currents. Now it can provide custom waveforms, and it has a trigger in and output options. It has also its own GUI, which is perfect for the most simplest applications. But if you want to do something more complicated stimulation patterns, you can just write your own code and upload it, and then you don't have to use this GUI. And then for the stimulation, you can use the Mint provided cables, which we personally found it's relatively thick, especially for a chronic mouse recording. So this is again a stimulation cable that was used by Sam in our lab, and it uses a Litz wire, and then we solder in our lab the Omnetics connector. And just to show you like a typical setup, like here you can see an IR sensor. So when the animal, let's say, run in front of this IR sensor, then this sensor can trigger the current driver, and then this current driver can send a current pulse to the micro LED probe, and also a trigger to your recording device. So everything is synchronized, and then you could record your neuronal activity using, again, whatever extracellular system you have. So, and then once you are done with your recording, then you really would like to recover your silicon probe and this precious device. And that's when these recoverable microdrives become extremely useful. So the first step before you would do your perfusion is to the reverse order of your chronic surgery. So first you break down the copper mesh. And once the copper mesh is removed, then you remove the metal bars. For the cement, you can just apply the heat, and then it will melt away the cement. And then you remove your PCB. Again, be extremely careful not to apply any tension on the flexible cable. And then once you broke down everything, then basically this is just an animation to show you how to use. So you move your drive holder a few millimeters away. Then you orient with your drive. So you are looking on from top for these two screws to be aligned. Once the alignment is correct, then you can move down your whole stereotactic arm, and then you can secure your drive with this side screw. And here you should be extremely careful not to tighten it too much, because it can break the plastic. And once this is secured, then you remove the back screw, and then you can slowly move up your stereotactic arm with your probe. So, and here you can see the alignment can take some time to find that perfect alignment. You can see I bump into this drive. Then you just stop, you start moving around things and make sure you get it right. And then once you find that, you just go down. Then you secure the drive from the side screw. Then we need to solder the PCB to the metal bar, and then loosen the shell screw. And then once this shell screw, which is here in the back, then you can start removing your device. And while you are doing any of this procedure, please try to keep an eye on the shanks all the time, because if you see any movement of the shank, so here you can see as I am moving up with this device. So if you see any movement of the shanks, or you start losing the parallelity of each shank, then you need to stop and then just look your environment and whether there is any problem or not around. 1 second. Okay. And so once after you recovered your probe, you can see here the probe is held by a helping hand. So you can soak it overnight in DI water. Then you can see here the 4 chunks are soaked in DI water. Then another overnight soaking in some kind of enzymatic solution, which can be just a contact lens solution, and then another overnight of DI water soaking. And sometimes you can have some tissue particles build up between the shanks, and then you could do some mechanical cleaning when you insert a fine needle between the shanks to remove those tissue particles, or you can just insert the probe into a phantom brain and then push further away the tissue or any mechanical particles from the recording sites. And so for data processing, so once you recorded your neuronal activity, you can detect artifacts if there is any. But again, with the newest micro-LED probes, you don't have to worry about any kind of artifacts. But if you do see artifacts, then it's highly recommended to remove these artifacts before any further processing. So here you can see, I just simply interpolated over during these artifacts. And with this procedure, we will lose data, but our spike sorting, the quality of the spike sorting will be much, much better. But even if you see such an artifact, you have some ways to reduce the artifacts. Again, the new artifact-free micro-LED probes doesn't have this issue, but you could use also pulse shaping. So instead of a square pulse, you could use a trapezoidal stimulation pattern or a Gaussian pulse or just a sine wave. So, and once you have a clean artifact-free signal, then you can run your spike sorting algorithms, and Kilosort 2 can again perform better with acoustic recordings and particularly with drifts. But again, any spike sorting software can be used. And there was another question from last week's webinar, whether the internal body heat is a factor in the accuracy of the data that we obtain during recordings with these probes. And basically, internal body heat will always affect the neuronal activity. It doesn't matter whether we use extracellular, intracellular device, like the heat itself will affect. But this brings up another great question, whether the micro-LED optoelectrode can heat the brain tissue. And the answer to that question is it's not really, because the amount of light that we are using is very low. It's in the power that we are using in the microwatt range, compared to a regular 100 micrometer optic fiber, where we are sometimes using the milliwatt ranges. And in addition to this, the silicon is a very good heat conductor. So the heat will be conducted by the silicon shank itself from the brain. But please keep in mind that long, like more than 10 seconds of continuous light stimulation can still heat the brain tissue. And so as a summary, like the micro-LED optoelectrodes are a perfect tool to investigate local microcircuit effects. And the new high-density micro-LED electrodes can provide an excellent spatiotemporal resolution. So here you can see the 4-shank 256 128 channel device that we used in an acute recordings. And here you can see the average ripple triggered LFP signal. This is recorded in CA1 and these channels are in cortex. And then we only stimulated on this shank, and then you can see this really local evoked local field potential response due to this stimulation. And I would like to thank to both Buzsáky and Yoon's lab and the funding sources. And I put together these useful links. And if you have any questions, please feel free to contact me, and thank you for your attention.